All right. So, why is radiometry and shading important? So we know that shading itself has a critical role to play in defining structures in the world. Right? It certainly is very important for our perception. So, for example, you can look at an image like that. Right? Obviously, it's an image. You don't know the three-dimensional properties of what you're looking at, but you can infer based on this image three-dimensional aspects of what you're seeing. Same thing, when we actually look at images of a lot of different things, but we have an idea of the three-dimensional structure, but more importantly, you look at an image like that, you not only know the three-dimensional structure, but you have an idea of the physical properties of this object. Right? You look at the image here and you start getting a feel for the textural properties that are present for that object. So the question is, how is that possible? And if we understand how is it possible, the more important question is, can we use that computationally somehow to infer properties about objects that we are imaging? Okay. So, well, we want to know that. And in order to understand that, first we have to build an understanding of the illumination process and its transference to what we actually acquire and actually can measure on images, which is pixel intensities. Okay? So what we want to try and do is understand if we capture an image and get a particular brightness value at a pixel, what does that mean? Right? You work with a digital image, you say, this pixel has a value of 100. What does 100 mean, right? What is the relationship of the value that you have on the pixel with respect to a particular object that's sitting out in space that you've just imaged? Okay. Now, of course, if we want to understand that, we have to understand a little bit about the illumination as well as the radiometric transformation process. So now, let's say that we have some point on a particular object in space, in the 3D space. That point is going to get illuminated by some light source. And of course, that point that's receiving a certain amount of light is going to reflect a portion of it, and that's what we're going to capture on our image. Okay? So the geometry we have seen. Okay? So we have seen the geometry that we have a point P in space. We understand the relationship of the geometric transformation it undergoes, and what is the relationship of point P in space to its projection P prime. We've already studied that. Right? But what we have not studied is the illumination or the intensity at which a particular amount of light is being transferred through the lens and onto our imaging plane. So in order to build a model that can describe that, we have to study a variety of things. One, we have to understand a little bit about the properties of the light source. Right? We have to understand a little bit more about the surface reflectance properties of any object in space that we are actually trying to image. We also have to understand about the shape of that surface, because that's going to dictate the orientation at which a certain amount of light is going to reflect off of that surface. Obviously, we have to understand the properties of the optics. We have to understand a certain amount of characterization of the camera that we are using, more specifically the exposure, right? Because we know that the longer the exposure, the more amount of light we are integrating. So we have to understand how that relates into this whole process. And then there are sensor characteristics. And when I talk about sensor characteristics, we are truly talking about the actual conversion process in terms of the amount of light captured, and the process of digitization that allows us to translate that into some pixel value, intensity value on a pixel. All right, so let's first define some basic terms as we try to understand what is this relationship. So the two basic components that we have to understand is radiance and irradiance. Okay? Radiance is essentially the energy that is carried by a particular ray of light. Okay? And more often than not, we define that in terms of power. Okay? Power per unit area that is actually perpendicular to the direction of travel of the light. Okay? And it's subtended by a specific unit angle, right? A solid angle subtended in space. And the units that we typically describe this is in watts per square meter per sterigine. Okay? So sterigine being defined as defining the unit subtended angle that we have. Irradiance, on the other hand, is actually the energy that is arriving at a particular surface.